Hi, I'm Angeline Lau. I'm from the Mathematics and Statistics Department of DLSU University. I'd like to thank the organizing committee for the invitation that allows me to give my talk and presentation for the 2021 DLSU Senior High School Research Congress. I'm excited to share with you how dynamical modeling and network analysis of complex systems can serve as our research possibilities or options, especially in this time of pandemic, and how helpful is this type of approach to be used in planning and establishing a better normal. The talk is divided into two parts. I'll start with how mathematical modeling can be applied to study epidemic spreading, and it will be followed by how this approach, similar approach, can also be applied to study diseases. So let us start with epidemic spreading. Topic in the area of epidemic modeling recently becomes very interesting and popular because of the COVID-19. So I will briefly go through the epidemic risk that we put ourselves in this new era, followed by presenting the systems model that can be applied to capture the spreading behavior of diseases and to assess interventions or control strategies that we can think of to delay or stop the spreading of diseases using modeling approach. So throughout the history, we have witnessed how epidemic disease can be devastating. They cause economic loss. It can even destroy lives as we experience now in pandemic. But in different time period, the effect is different, and how fast the disease spread is also different. Okay. So this is a consequence of globalization. So we are experiencing now a new era of epidemic risk, where infectious diseases spread in a borderless world. So why it's borderless? Globalization increases the speed and volume of humans, non-humans, like animals, plants, and product mobilities because of the advanced transportation system that we have. Okay. It also introduced infectious diseases in new locations that changes the geographic distribution of disease vectors. Hubs like airport, train stations, shopping malls also created an option for the population to be concentrated, and these increase the contact rates of this population. Okay. So if this is for a disease epidemic, this is not good because you increase the contact rate and lead to higher chances of being infected. But if we are speaking of in terms of information epidemic, then this is a good option. This is a good hub to disseminate information. So these hubs are conveniently connected, okay, with the advanced transportation and technology and transportation systems that we have. It allows people, plants, and animals to mobilize from one hub to another hub very convenient. If one node is infected, the other nodes that are connected to it might also be infected based on the strength of their linkages and connections. Again, if one hub is infected, eventually lead to epidemic spreading of diseases, since we saw in our previous illustration that most of the hubs, for example, countries, okay, are really interconnected by the flights. Another factors that can contribute to epidemic spreading of diseases is climate change. Climate change also contributes to the global spread of infectious disease. As the Earth's climate change, the habitats are altered, and disease can spread into new geographic area because the species might try to find a new habitat that is suitable for them to live. And this exposes new populations to new disease threats. With global warming, it changes the behavior and development of insects, bacteria, and viruses, okay? And exposing the populations to uncertain disease threat. Take, for example, the effect of global warming to mosquito. Warmer temperature usually accelerate the development of mosquito, reduce the incubation time for the mosquito to become infectious. With warmer temperature, this also implies that more people will be storing more water in their containers that can serve as a breeding sites for the mosquito. Moreover, again, warmer temperature prolong active season, okay, for mosquitoes. And with high humidity, it also improves the chance of survival of the mosquito. So what is the spreading behavior of diseases? It's only when you understand the behavior of how a disease is spread, that's the only time you can design and strategize how to avoid or eliminate it. So there are two components that make a disease spread rapidly. One is how high is the infection rate in contracting each individual and how easy it is transferred. So what are the common precautions that we are doing now? What we do now is quarantine or social distancing. We avoid places where there are many people, okay, until it passes through enough people, eliminating the disease, which we call herd immunity. Mathematical modeling plays an important role in the efforts that focus on predicting, assessing, and controlling potential outbreaks. Proposal of how this situation can be solved. Over the past few years, a vast number of approaches have been proposed looking at the problem from different perspectives. And we can actually categorize them into three general clusters. First one, the leftmost, is the statistical methods for surveillance of outbreaks and identification of spatial pattern in real epidemics. The second category is the mathematical models within the context of dynamical systems, which we also call state space models. This is used to forecast evolution of hypothetical or ongoing epidemic spreading. The third one is through machine learning or expert methods for the forecasting of the evolution of an ongoing epidemic. So we learn from the data that are driven from the web base, and then we learn from this data and try to forecast and predict or project the behavior based on the current collected data. In particular, we have the following epidemic models. So let us start with the classical approach. The compartment model approach. Under this approach, we have the basic SIR compartment model. Individuals are assumed to be well mixed or homogeneous and are classified only according to their epidemiological status. Okay, so we have the susceptible status, infected status, or recovered status. And then we also have the vector-borne compartment model, where we separate two types of homogeneous clusters. So here we have two subscript, H and M, that denote human and mosquito respectively. So both host and vector individuals are assumed to be well mixed or homogeneous. However, the mosquito needs to interact with the humans in order to infect the human, okay, with dengue. In this slide, we are showing a simple illustration of how a simple SIR compartment model works. We focus on the first equation for the change of the susceptible population with respect to the change in time. Okay? So this change in the population with respect to change in time is given by its own population growth, mu n, okay, minus the rate at which it is infected by the infected population upon interaction, represented by beta Si all over n. And then this is also subtracted by the natural death of the susceptible population, represented by mu times S. Similarly, you can represent it to the infected and recovered population. And if we, after solving this systems of ordinary differential equation, after we integrate all of this, okay, we can actually generate the plots shown here on the right. So the black curve denotes or represent the susceptible population, and the red curve represent the infected population. What we can observe here is that at the first part of the simulation, okay, the black susceptible population density increases, whereas the red infected population is 0. And then as the red infected population density pick up here, increases, the black density population started to drop, okay, as the red infected population density increases. Okay. As the red population density started to dampen at the last stretch of the simulation, this is also observed on the black susceptible population density. Okay. And then these illustrate or beautifully illustrated the relationship, okay, or the dependent relationship of all of these compartments or variables S, I, and R. Next, we introduce the basic reproduction number. Okay. The basic reproduction number R naught is the average number of secondary infections produced when one infected individual is introduced into a host population where everyone is susceptible. In short, this indicates the ability of the infection to spread. Hence, the higher the value of R naught, the more infectious the virus is. And in epidemiological transmission model, this is usually taken as the threshold parameter. Here we see a time-varying estimation of the effective production number, okay, where the lightest ribbon pertains to the 90% credible interval and the darkest ribbon pertains to the 20% credible interval. This data is collected or last collected on April 5, 2021. Note that in identifying the changes in the basic reproduction number, the changes can be due to the biases, or the biases can be due to delays in the reporting, okay, in our country, and changes in testing effort, and increases and decreases in testing effort also has some effect in the increase and decrease of the computation of the basic production number. Okay. That is why at different stages, we might have different basic reproduction number. And then at different locations or area, different basic reproduction number is also computed. So how do you compute the basic reproduction number? Okay, this is the basic algorithm, okay, how we compute the next generation method to compute the basic reproduction number. So we need the F, which is the transmission matrix, and V, which is the transition matrix. Okay. So the transmission matrix represents the rate of appearance of new infections. And the matrix of transition represent the rate of transfer of individuals into and out of the infected compartment. And then we can use this theorem, Van den Drisch and Vatmov theorem, to determine the local stability at a specific disease-free equilibrium point. Okay, so if the R naught computed is less than 1, we can conclude from this theorem or prove through a theorem that at this R naught and at the given disease-free equilibrium point, it is locally asymptotically stable, or the disease will actually die off. And this is computed by the R naught, which is represented by the spectral radius, okay, of the next generation matrix. So we are going to compute the spectral radius of the next generation matrix FV inverse. Okay. And the spectral radius is simply the largest eigenvalue of a matrix A, okay, in absolute form, as shown in this equation or formula. And then the transmission matrix F is an m×1 matrix where each of its elements is the rate of appearance of new infectious individuals in the given compartment X sub I. And we can compute F by the partial derivative of each of these elements F sub I at the given disease-free equilibrium point X sub O with respect to the partial derivative of different compartment X sub J. And this is how we compute for the equilibrium point or fixed point. So to compute the equilibrium point or fixed point of a dynamical system, of a systems of ordinary differential equations, what we do is we set the rate of change to 0. Okay, we set the rate of change to 0, and then we can solve for the respective compartments X sub J or X sub I. When we compute them, we will generate this vector of the compartments wherein the rate of change is equivalent to 0. Okay, and it is a disease-free equilibrium or free disease equilibrium if the compartments containing the infection will be equivalent to 0. So this is a simple illustration. We have a systems of simple SI model. To compute the disease-free equilibrium, we will set these two equivalent to 0 and solve for S and I. Since this is a disease-free equilibrium, hence I, okay, will be equivalent to 0. Okay? And then we compute the transmission matrix F is equivalent to beta S. Okay? And then we substitute the disease-free equilibrium point, and we will derive or arrive at this value, beta times lambda all over mu. So again, F represents the rate of appearance of new infections. So this is the rate, the corresponding rate. Next, we solve for the transition matrix V. Okay? Transition matrix V is an M by 1 matrix with each of its element V sub I denotes the rate of transfer individuals into and out of the compartment. So it's actually the difference of V sub I minus and V sub I plus, where V sub I minus is the rate of transfer of individuals out of the compartment X sub I, whereas V sub I plus is the rate of transfer of individuals into X sub I. And similar to how we compute for F, V is equivalent to the partial derivative of V sub I at the given disease-free equilibrium point with respect to the partial derivative of each compartment X sub j. So if we follow the computation of the formula, we will arrive at mu plus d for V, and V inverse will be 1 over mu plus d at the given disease-free equilibrium point X sub 0. Hence, we can derive at the next generation matrix, which is a product of the two matrices. Okay? So we arrive at the next generation matrix, and then we compute the spectral radius of this generation matrix, okay, which is beta times lambda, all over mu times the sum of mu and d. Okay, if that value or the spectral radius of the next generation matrix is less than or equal to 1, then we can conclude that it's locally asymptotically stable. Okay. Or in other words, the disease dies off. Okay? If it's greater than 1, then we can conclude that the disease persists. This type of modeling approach or process of solving the equilibrium and determining the R naught and proving that this R naught is either locally asymptotically stable at a given disease-free equilibrium or unstable, this can be applied to various of epidemic spreading type of problems. Like, for example, in this paper, we applied that in studying or analyzing the dynamical models or behavior of tuberculosis in the Philippines. In this study, we obtained a disease-free equilibrium, like what I mentioned or discussed earlier, and we found that it is actually unstable at the given disease-free equilibrium. Okay. This implies that a continued challenge to control tuberculosis in the Philippines is very important. And the population is assumed here, okay, in this compartment. We have a homogeneous compartment and we have 6 compartments. SA is the susceptible and immunized group. SB is the susceptible and partially immunized group. LA is the slow latently infected group. LB is the fast latently infected. I is the actively infected and undetected, whereas T is the actively infected, detected, and treated. So the individuals can transfer from one compartment to the other compartment through the arrow, to the flow of the arrow, and the corresponding rates of transfer are represented by the parameters stated behind these arrows. Another example is we apply this also to study the transmission dynamics of avian influenza A in the Philippines. So as a better alternative to culling the domestic bird, we actually try to see or propose alternatives, okay, to control and reduce the spread of avian influenza. So we modeled the efficiency of implementing isolation, the one on the left, and then on the right, that's the proposal of implementing the vaccination strategy to the poultry. So in the vaccination model, which is on the right, showed that no matter how effective the vaccine is, if the majority of the population is not vaccinated, it is hard to control and prevent the infection. Okay. And it appears that this approach is actually more expensive than the isolation strategy. Moreover, we also showed that the isolation strategy is actually a more preferable choice. Where else can we apply compartment modeling? So in recent years, online social platforms have been rapidly developed, which have greatly changed the way people communicate. So we can easily spread an information efficiently through social media platform. Just as the social media can bring people together for constructive reasons, social media can connect dissatisfied and misguided people together. So this can fuel negative attitudes and beliefs. In this work, we try to study information spreading process on social networks. In the past studies, most of the model they build is they try to investigate the spread of rumors without considering the influence of the simultaneous spread of the truth. So in this study, we consider both spreaders of truth, which is those on top, together with or the coexistence to the spreader of rumors, which is shown here below. And we want to investigate how their coexistence affects their spreading abilities. So we formulate two mathematical model, the SS model and the ES model, based on the popular SIR model, which is extended to SEIR model, where E there is the exposed population. In the spreader model, what we see here is the interaction where the spreaders try to influence the opposing spreader. Okay. Whereas in the ES model, which is the exposed spreader interaction model, the spreader tries to influence those who are exposed individuals from the opposing side. And to study the spreading process, we applied similar approach. We try to compute for the reproduction number and determine at what parameter will the situation become rumor-free, where the rumors will actually dies off, and at what parameter will the rumor become epidemic. This is an illustration of the numerical simulations that depict the effect of changing parameter alpha. So what is parameter alpha? Alpha is the effectiveness of the spreaders to educate the ignorant people with the truth. Okay, so we try to control this and to determine how should be the strength or the effectivity of the spreaders of the truth to these ignorant people. Okay, in order to have more people being exposed to the truth and become spreader of the truth. In these simulations, we try to change this parameter, delta, which pertains to the effectiveness of the spreader of truth to convince the spreader of rumors to stop spreading rumors. How convincing or how much effort should this spreader of truth be in order to stop the spreader of rumor to stop spreading rumors? Now we move on to the applications of optimal control theory. So this is an extension of our work for the avian influenza virus. Okay. We applied optimal control approach to study the prevention of H5N6 outbreaks. This is a similar model where we have the isolation and vaccination model, but we applied optimal control. To formulate an optimal control problem, you need an op control variable represented by U. The constraint will be your SIR model, the differential equations. And then what we want is to minimize or maximize, or in short, to optimize a cost function defined by J. where you have your state variable and your control variables. This is an example of a model that we have in this study. Okay, this is our cost function. So what we try to do is we want to minimize the number of infected population given that we apply this control strategy. And then this cost function, while we are optimizing it, okay, in particular we are minimizing it, we want it to satisfy this condition, which is the SIR model or SER model of the SVI model. This is for the vaccination. While satisfying these constraints, okay, or different differential equations, the goal is to find a particular variable u and state variable x as such that this will be satisfied and this will be optimized. In this slide, we show the simulations of the optimal control model. The one we have here, U1, U2, these are our control parameters or control variables. U1 pertains to the isolation control, and then U2 pertains to the treatment control. So this is the function representing the isolation and treatment control. Without control, this is the population of the infected birds. In the applications of the optimal control, we were able to minimize it as such with these control strategies. And with different varying birds population, B1, B2, these are the different simulations that can be generated with different optimal control values. Similarly, this can be applied to the vaccination strategy. And this is what we generated. U3 here is the one we have here. Okay, this is the vaccination prevalence control. So this is the function representing the vaccination prevalence control with respect to time. Okay, and this is the vaccination efficiency control, okay, with respect to time. And then we do this simulation at varying level of birds population B3, B4. Okay, and this also changes the control functions and the population generated for susceptible, infected, and vaccinated. This approach can also be applied in biology and medicine. For example, control and modulation of neural and motor systems, control of cellular and molecular systems, and control of diseases or personalized medicine. Now, moving on to graph theory and hypergraph's approach of modeling epidemic diseases. Network model is formed by at least two basic components, and these are the vertices and edges. The vertices are represented by the nodes or the circular colored nodes that you can see there in the slide. And we have the lines representing the edges. Okay. So vertices are connected by edges defined by their relationship of interest, such as, for example, by trade or relationship or being friends. Okay. If you're a friend to one another, so you can be linked to one another. And then infectious diseases are modeled to spread via this edge, okay, in this model. For example, we have here the SIR model, S represented by the blue nodes, I represented by the red nodes, and R represented by the recovered node. So given the differential equation, you can also represent it using a network graph, okay, or a network model. And we can even study the topological properties of this network model. For example, we can find the shortest path and network diameter to determine the degree of connection between these nodes, okay, in your network model. We can compute the degree centrality, degree distribution, degree correlation, okay, to identify, for example, which individuals play an important role in spreading the disease or information. And based from this, we can actually decide how to control the spread based on the network properties. Again, This type of network model can be applied to social media map in studying the dynamics of how information, especially health in communication, are actually being promoted or spread. So based on the contact and interaction of the nodes, the dynamical state of the vertices may change accordingly, as you can see from the animation. Network models are useful in tracking sources and identifying the targets based on the arcs, edges that links the vertices or nodes. And based on the type of assumed network, we can also illustrate them using simulations. Next, we move on to meta-population model. So in meta-population model, we have two patches or two layers. In each layer, they are homogeneous. So the entire population is divided into subpopulations, as you can see from this illustration on the left. These subpopulation can actually interact with one another. And this, as a whole, is a heterogeneous network. These models keep track of the number of individuals at different locations or different patches. Okay. Note that these subpopulations or individuals from these subpopulations are mixed homogeneously as shown here. Okay. You can have another network within the subpopulations, and this is the larger network which represents the relationship of these subpopulations. With each subpopulations, individuals are classified according to their dynamical status. Here, most likely the red pertains to the infectious and the yellow one to be susceptible. So you can see that there are more infected people in this subpopulation than in this subpopulation. And then when people tries to migrate, if the infected population tries to migrate here, it will generally affect also the subpopulations. Hence, if you want to control the disease in a specific subpopulation, for example, in this network, how are we going to strategize? By knowing the structure of the network and representing them in terms of subpopulation. For example, this is your point of origin and you want to visit this destination. If we are going to consider using the shortest path, what is the shortest way or fastest way to arrive at this destination? You might end up using the blue curve. Okay, you might pass through a subpopulation with a lot of infected individuals. Of course, you want to avoid that. You don't want that. Hence, what you want to do is you will try to find an alternative path, okay, as such that you will not pass through any of the major infected areas shown by these dotted arrows. Okay, here's another representation of how we can visualize or at least represent the extracted information that we can get from, for example, from generated from the hospitals or barangays. Okay, so in Figure A, we can illustrate them as in a macroscopic level, where we have the locations, the household, or the institutions, and of course within this institutions, household, there are people within them. And we can also show how these locations can be interconnected with one another. So for example, there are people living in this area that usually goes to work or to school or to church. Okay, then we can link this institution or locations, okay, from one another. In Figure B, we try to put all the locations on one side and the people on the other side, and see how they can actually be connected to these locations. Lastly, okay, in Figure C, we showed the unipartite projection of the bipartite network, which is shown here. In particular, we focus on the people. Okay, so here we show different transmission rates and weights on the network depend on the location, which is color-coded, and type of interaction of these people. Maybe these people live in the same area, in the same location. However, because they travel, and they have an interaction with these people in another location. And if the linkages or the interaction is strong between these two, if one of these is infected, it's possible to infect these people and infect also people in that given location. Okay. Next, we move on to agent-based modeling. Individuals for spatial space modeling are located at different locations. So you have spatial aspects, or you can specify the specific locations or area. Okay? And the transmission of infection between the infectious individuals and a susceptible individual will be defined by the distance, okay? Distance x, for example, and the probability of their infection can be defined by some k of x. The one below is an individual-based model where each of the agents have a specific role, and you have to explicitly define a set of characteristics, including their epidemiological status, spatial location, and their interaction preferences and their behavior traits. Everything has to define. Okay? This is an illustration of how one can use agent-based modeling. Okay? So the green one are the HIV negative. Okay? Red one are those who are HIV positive, and the blue ones are those undefined. Okay. So you'll see that once there are more interactions between red and green, okay, there will be more red at some point. Okay. Agent-based modeling can also be applied to study, for example, or model complex life cycle of cyanobacterium, okay, in a shallow reservoir. So it's not limited to epidemic modeling. Okay. So as you can see here, that agent-based modeling can take into account details such as the transportation infrastructure of the simulated area, the mobility of the population, demographics, the epidemiological aspects such as the evolution of the diseases within a host and transmission between hosts. Next, we move on to the application of deep learning and artificial intelligence. Okay. There is a large data sets known as big data available in the internet. And to quantify these data that describe social phenomena and behavior patterns, machine learning and deep learning approaches are being applied to automate the extraction of information and analysis of data. Social communications, platforms, and research engines such as Google and Wikipedia provide web search query that are capable of tracking and estimating disease activities. This internet-based platform have revolutionized, okay, in the way that we get the information, which are actually promising, okay, for data mining and can be used for real-time surveillance of web-based tool. This is an example from a study by Ginsberg that exploited the aid of search query of Google platform for early detection of influenza epidemic in US. The authors used around 50 million Google web queries related to influenza symptoms between 2003 to 2008. And a linear model using the log odds of a visit of physician in a certain region and a log odds of related search query is submitted to the same region was fitted using publicly available data from the CDC's US Influenza Sentinel Provider Surveillance Network. Okay. So they also try to validate it using another set of data from CDC. In this study, they try to predict dengue by the webs through the tweets that are being collected. Okay. So if somebody tweeted, I have fever, I have high temperature, okay, or I have dengue, okay, then this information are collected and it's used to forecast, to estimate and forecast or project what will happen in that area in terms of dengue. Okay. And these types of model will be helpful to government officials for them to immediately identify which area are infected by dengue and start to do some actions, okay, to control the spread of the um, mosquito. This is another study where they try to detect influenza and predict them through social networking sites. This is their framework. They collect data from CDC and web blogs. Okay? And from web blogs, they try to extract keywords, which is through text mining. And then from these keywords, they try to identify which location part has reported influenza. And then they will cross-validate it with the data they collected from CDC. For diseases, last year, it was reported that one can also use mass spectrometry to detect early infection of COVID-19. Since mass spectrometry data are not so expensive to generate data, and it is actually an instrumental machine that is accessible by major hospitals, it is now considered as important source of data. Okay? Back then, okay? Because back then it was actually very difficult to to analyze samples whether it has COVID or if you're COVID positive or negative. Okay. And the highlight there is not the COVID, but of the mass spectrometry. So one can generate a platform or a model that can detect through machine learning approach, through support vector machine approach, whether whether you will have COVID positive or COVID negative. So in this study, we applied that to detect pancreatic cancer through the data feeded into the platform, which is a mass spectrometry data. And then for diseases, we can also apply similar dynamical models to study diseases. For example, we applied that in studying brain-related diseases. We apply systems of ordinary differential equation to study the interactions of proteins and genes that are connected to the amyloidogenic processing, okay, of Alzheimer's disease. We extended it with compartment modeling of the amyloidogenic processing in Alzheimer's disease. So here we try to track the activity of the genes when it's migrated or transferring or traveling from one compartment to the other compartment. And in this study, we perform stability analysis for the ODE model that we built in the first study that I showed earlier. So similar to what I presented earlier, we computed for the equilibrium point, and then we identify that whether at this given equilibrium point, will we have an asymptotically stable system or unstable system. We also use it to study the relationship between type 2 diabetes and Alzheimer's disease. So we have here an insulin resistance pathway in relation to type 2 T2D and AD. Okay, so the pathway is composed of insulin signaling that inhibits gluconeogenesis in the liver through the disruption of mTORC2 binding. And we have the insulin resistance also leads to both A beta plaques that we showed here. Okay, and in this model, we consider factors or markers like JNK, IKK beta, ERK2, okay, which are hypothesized to be contributory factors to the development of Alzheimer's disease. We also applied it to study brain metabolism, as shown in this illustration. We also applied it to study cancer diseases, okay? And in this study, we want to test, okay, through mathematical model, how the cytotoxicity activity of Raphanus sativus can affect, okay, three cancer diseases, namely colon cancer, breast cancer, and leukemia. To conclude, so we have presented here different model systems to understand mechanisms by which the epidemics spread. And we also use the model to evaluate the effects of interventions, to predict epidemic outcomes, and to forecast future course of outbreaks. These modeling frameworks provide valuable information in making public health policy to prevent and control epidemics. They can also serve as effective and sustainable global surveillance tools and mechanisms to monitor outbreaks and to facilitate rapid and effective responses. Okay. In terms of diseases, this modeling approaches or framework can be helpful in designing personalized medicine or in understanding a specific biological systems of diseases. To end, I'd like to acknowledge the Center for Complexity and Emerging Technologies, Sensors, Systems and Computational Biology Research Unit, and Brother Albinus Peter, FSC, Brother C. John Lynam, FSC, Professorial Chairs in Mathematics.